So we were working through allylic strain on Tuesday. So we were looking at this. Sorry, I'm going to do it this way. So we're going to share this. And then we're going to make this big. And we're going to share this. Right, so we were looking at this structure and trying to draw the minimized A13 conformation that I think we had. So I think it looks something like this. We have our double bond. We have our hydrogen in plane. And then that would put the methyl group up in the O-benzyl group down, I do believe. Right, because of our, and then like the rest of it. All right, and then the hard part is just kind of knowing that this group is bigger than a methyl. All right, so that means that the methyl, the top side is less obscured than the bottom side. So we're going to add our boron to the top face, which would give us an alcohol that is up, a methyl that is down, a hydrogen that is up. So we'd end up with this. Which, thankfully, matches what the product from the actual experiment was, right? So we've got our OH is up, our hydrogen is up. So this matches what we drew. So we can use A13 strain to predict how groups will approach a double bond. So we can do that. Here's another example. This is doing an iodolactonization. So first we do a Wittig reaction where they use sodium hydride as the base to make the ylide. Right, that makes the cis double bond. And then they use I2 to cyclize onto the what's it called? Onto the double bond. So we can use A13 strain to predict which side the iodide is going to add to, which is then going to allow us to figure out how we're going to make the stereochemistry at this carbon and this carbon. So I have it kind of drawn out here, but it might be a little cluttered. So if we were to just kind of draw a simplified version of this molecule, right, we don't need the whole thing, right? So we have our double bond, right? We don't need all of this stuff, right? That can just be, that's the little squiggly line that we have drawn. But yeah, we don't need all of that. We have our double bond, right? And then we have this, right? So not cyclized. So we minimize A13 strain at this carbon, right? That's going to be putting our hydrogen inside, right? And then we need to figure out which group is up and which group is down. So if we look at it, oops, sorry. If we look at this, where we have the hydrogen back, we want the hydrogen in plane. So we're going to kind of turn around this. So the hydrogen comes in plane. That methyl group goes up. And then the group with the acid goes back. Right? And now the methyl group is the smaller of the two groups, right? The methyl group is smaller than that longer chain. Feel bad with the screen in front of you.
No, you're good. I'm calling my computer, so.
There you go. Now you can see me. The one person can see me. So now the iodide is going to approach from the side of the, what's it called? Thinking. Of the methyl group, right? Because the methyl group is smaller than, right? So this methyl group is smaller than this whole chain, right? So the iodide is going to come from the side of the methyl group. Okay, swivel here. Which is going to lead to what I have on the slide. I'll just draw it out, right? Where you have iodide is up, and then you've got your hydrogen in. Oops, I put a carbon there. And you have your hydrogen in methyl up. Like that, right? So now your oxygen comes from the bottom face, right? It's kind of enforced by two things. One, the iodide is up, so the oxygen has to come from the opposite side, has to come from the bottom. And also, right, the way that this chiral center is oriented, right, the oxygen is oriented down, right? It's oriented away from you. So that's also telling it has to come from the bottom. So all this stuff together ends up with you having iodide, and then you get O. That. So that does match what I kind of have drawn on the slide. Right, this is a little bit neater. Okay, but there's your iodide, your iodonium ion on the same side of the methyl group. And then your chain coming from the bottom to add to that and push electrons onto the iodide to get you this. If we try to do it the other way, right, where we put the methyl group on the inside, right, and then have the iodide come from the hydrogen, you have a large A13 interaction where that methyl group bangs into the rest of the chain on the other side of the double bond. So we can use this in like ring closures as well. We can predict which side of the double bond, if we activate it, we're going to add our group to. Seem reasonable? All right, so then there's another thing where you can do something that's that instead of just minimizing A13 strain, you orient your molecule so that the so that there's a group that is perpendicular to the double bond so that it can interact with the carbon-carbon double bond, the p orbitals, to help weaken that bond. So it speeds up the rate of the reaction. So if we think about what a double bond looks like, right, the orbitals, right? So if you remember, a double bond, you have, right, the 2 pi bonds, right? And that makes a double bond. That, I was going to say equals, but it's going to look like a double bond, equals a double bond, right? So you have 2 pi bonds that line up with each other that make the double bond. So in this model, where you have to worry about the reactive conformation, you are trying to put a group perpendicular to the double bond, so the electrons in the carbon X bond line up with the pi orbital. So this is reactive conformation. Right, so what you're trying to do is you're trying to have your double bond and then have the electrons in whatever your carbon X group is, have these electrons line up with the pi bond. So they're able to donate some of their electrons to the double bond. So this donation, donates, slash stabilize, donates electrons to the double bond. To weaken it. Which sounds funny that you're adding electrons and weakening a bond, but these electrons are going into something called an antibonding orbital. And so when you put your electrons in that antibonding orbital, it weakens the bond. So this can donate electrons to weaken the bond, or you can stabilize, spelling's hard, where you can stabilize intermediates. We're going to pretend that you can read that. Right. So let's say you're starting to make a carbocation. You're starting to make a positive charge. Those electrons in that X bond, in that carbon X bond, can interact with that positive charge and help stabilize it, making it so the reaction goes faster. Right, so lining up the X group with the carbon pi bond increases the rate of the reaction. So if that's the case, when we go to minimize A13 strain, we want to do it in such a way that we have our X group lined up with the pi bond. So the example I have on the slides here is that you have your X group lined up with the pi bond, and then the hydrogen is inside. It's not 100% like eclipsing the double bond, but it's still inside the double bond towards the R group. Right, so again, we're looking at the double bond on the side where this R group's coming out at us, right? And so this R group is close to the hydrogen, and we have our X group that's going to speed up the rate of the reaction lined up with the double bond. Or we can do it where the X group is lined up with the double bond, but the R group, the other group on the chiral center, is inside towards the group on the double bond. That has more A13 strain because you have two large groups together. So when you have a group, like usually it's a silicon, which is the example I have here, but there are other groups that do it. If you have a group that you have to have a reactive conformation, where you need to have it lined up with the double bond, you want to stick that smallest group inside towards the group on the double bond, right? Because that minimizes A1-3 interactions because you're sticking a small thing inside by a larger thing. So, kind of the classic example of this is these epoxidation reactions with allyl silanes. So you have your silicon and your double bond, and when it's trans, there's not a lot of A1-3 strain, right? But when you have a cis double bond, you have a lot of A1-3 strain, and you favor putting your epoxide on the opposite side from your silicon. So if we were to draw, so we picked an enantiomer, right? We'll pick the enantiomer that they draw in the product, right? So dimethylphenyl. And they end up on opposite sides.
We can't see what you're writing.
Oh no, I forgot to share it. Thank you. I hate my life. There you go. Much better. My headphones didn't work. We're getting to share screens.
Why aren't they? Is it an Apple computer you're trying to connect it?
It's just not pairing for some reason this morning. They're just not connecting to each other. I might have to factory reset the headphones, which isn't a big deal, but okay. So if we do this, we can draw our structure. We can draw the reactive conformation, right? Where we're gonna have, we put our double bond in plane. We say this is back, this is back. Puts our silicon up here. Wait a minute. It's probably just easier to look at it this way, right? We've got our silicon is up, our hydrogen is back, right? So our silicon is straight out at us, which is perpendicular to the double bond that's in the plane. So then our MCPPA has to come from the opposite side because the hydrogen is the small group. Or the methyl group's the small group. Let me see if I can draw it better. I'll make it suck less, right? So we're going to have hydrogen in plane. That's going to put our silicon up. And it's going to put our methyl group back. And, yep. So let me make sure I did this right. 1, 2, 3. This is R. 1, 2, 3. We'll switch this. We'll say H is over here. 3. 1, 2, 3. This looks like it is S, but it's R. So yeah, so this is right. Can you see that? Okay. So basically, again, I just kind of turned it a third of a turn to move the hydrogen in plane. That made the methyl group go down and the silicon come up. So the MCPPA approaches from the side of the methyl because the methyl group is way smaller than the silicon group, right? So the silicon's blocking the top face. It comes from the side of the methyl group. And that silicon is still kind of lined up with the double bond. So these are all examples of using a chiral center at the allylic carbon to kind of to minimize strain and have your group approach from have your nucleophile or your reagent approach from the most open side. Now, there's another thing we can do that's a little easier to see, and that is just doing coordination. Just having your group. Come on, you can do it. Thank you. Just having a group that can coordinate to your reagent, that will just hold your reagent so that it will approach from that side. So this is using coordination to drive your selectivity. So the quintessential example of this is the Henbest effect, where you have a cyclohexanol or cyclohexenol, and you use the alcohol that's in the ring to direct where the reagent is going to go. So let me draw it out because this example is a little opaque. Right, so you have, we'll make it up, an oxygen that is up, and you treat it with MCPBA. That oxygen interacts with the MCPBA and holds the MCPBA on the top side of the double bond. So it holds the MCPBA on the same side that the alcohol is on, which leads to the epoxide in the alcohol being cis. They didn't use MCPBA, they used something pretty close. So whatever. If you put a group on the alcohol, so if you get rid of the hydrogen on the alcohol, so if you make it an acetate, now you've lost that hydrogen that can interact with the oxygens on the MCPBA, and now you get a mixture of isomers, with the anti-isomer being favored. So this is the favored isomer here, and this is the favored isomer here. So when you have an OH, you get the cis isomer, right, where the epoxide and the alcohol are on the same side. When you have an acetate, you get the anti-isomer, where the oxygen, where the acetate and the epoxide are on opposite sides. So the bottom one is easy enough to explain, right? You have the acetate, which is a large group in air quotes, and on the other side of it, you have a hydrogen, right? So your MCPBA comes from the side of the molecule that has the hydrogen because it's smaller, right? So that's basically what we were just doing, right? You have a big group and a little group, you come from the side of the little group. When you have the alcohol is able to actually interact with the MCPBA. So if you remember what MCPBA looks like, right? You have all these oxygens. So what happens is when you have an alcohol by your double bond, that alcohol actually interacts with one of the oxygens of MCPBA. So you have like you have this hydrogen bond that is going to help hold the MCPBA on the same side of the molecule as the alcohol. So just that small hydrogen bond lets that MCPBA be held to the top and then favors one product over the other. So you can just coordinate. So this works with alcohols a lot. It can work with amines. So there's a lot of different reagents you can direct with an allylic alcohol or an allylic amine. So here, this is a homoallylic direction. So I don't know if you guys remember the term homoallylic. So let's do that real quick. Get everyone on the same page of Wakefield's weird terminology. All right, so you've got this is an allylic alcohol, right? Where again you've got your vinyl carbons, and then this is your allylic carbon, right? Homoallylic means that there's an extra CH2, right? So way back in Organic 1, like one of the first things I taught you was that like when you go from butane to pentane, they differ by a CH2, right? And I said those were homologs. They're part of a homologous series where you just add a CH2. So this is a homoallylic alcohol. Oops. Where the difference between it being an allylic alcohol is there's an extra CH2 between the allylic carbon and the alcohol. So in this example here, where they're doing this epoxidation on a steroid, right, you have this alcohol right here, and it's homoallylic to the double bond, but it's still close enough that it can direct the epoxidation. So with MCPBA, they get a 2-to-1 mixture of the syn epoxide, where the epoxide is on the same side as the alcohol. But if they change the reagent, if they use vanadium acac, you get a 100-to-1 ratio. So you can still like play with your reagents to see if that to try to change your selectivity. So I guess I should. I guess none of you know what acac is. Right. So when you see acac, there's a small duck yelling at you. Acac. No, well, that's Aflac. I got high quality humor here. I'm a dad now, so like the dad jokes make more sense. So whatever.
That jokes are amazing. It's totally fun.
So this is acetyl acetate. So, or acetyl acetone, right? It's acetone, and then you add an acetate to it. So it's acac. So it's just a ligand that sticks onto the metal. But I feel bad, like just saying a term and being like, they'll figure it out. I feel like I should take a second and just explain it, even if it's small. So you're not like, what is acac? But this reagent coordinates more strongly to the oxygen, so it gets directed to do a syn addition. All right. So, if we look at this, here's an example from a synthesis where if they use a 5-membered ring and they use osmium tetroxide and T-meta, which is tetramethyl diamine, which is in a box, bottom, they get 25-1 favoring the syn dihydroxylation, where you put the two alcohols from the same side. If you just use osmium tetroxide, a catalytic amount, and NMO as an oxidant, you switch your selectivity, you get 1-4, where the favored isomer is the anti-product. And they attributed to this to the fact that T-meta can act as a ligand on the osmium. So they said that they have their osmium tetroxide. It's going to make like an inorganic chemist cry what I'm about to do, right? And then you just have your amine act as a ligand. And it's going to be the crappiest ligand in the history of ligands ever being drawn. Right, where you get something like this, right? And now you've got these nitrogens that have lone pairs that can interact with the alcohol. So osmium tetroxide by itself doesn't want to coordinate to an alcohol, but you add T-meta to it, and now this lone pair can hydrogen bond to an alcohol, to an OH, which then allows it to be directed from the top face. Hey now, sorry Zoom, computer's being dumb. No. It's getting worse, not better. What are you doing? I don't know why the whiteboard went away. There we go. We fixed it. All right, so these will allow that osmium to be directed from the top face, where if we go with osmium, if we just use osmium tetroxide, it doesn't coordinate to the alcohol, so it goes to the other side. Why is it doing that? There we go. Okay. So when you have osmium with the nitrogens on it, this is ugly, but it works. Those nitrogens make a hydrogen bond and hold the osmium on the top side. When it's a really bad hydrogen bond, but you get the idea, H bond. So now you're holding your osmium that's going to deliver your alcohol or your oxygens to the top side. When there's no T-meta, now you just say oxygen is bigger than hydrogen, so then my osmium comes from the bottom side. So you can just tweak your reagents to get a directing effect. So sometimes, right, a lot of times things are kind of like guess and check. So let's say on your test that is next week, right, it would be hard for me to just randomly give you a reagent and be like, hey, predict how this is going to work, right? But I could, let's say I could give you something like this, right, and be like, okay, what is different about these, right? And if you're like, well, I don't know what T-meta does, but it must make it so the osmium coordinates to the alcohol. Right, so sometimes you can look at your product and then you kind of reverse engineer a rationale for the selectivity. So sometimes it's hard to go from, rationalizing what your selectivity is going to be at the end. But once you have your selectivity, it's usually a lot easier to think about, like, okay, since this happened, how was the molecule arranged? How did things interact? So while I couldn't, give you just a random molecule and go like, hey, predict how this is going to work a lot of times, unless it's something that like we explicitly went over, I could give you something new that you hadn't seen and show you the answer and say, hey, explain to me how you get there. So all of these examples that I've done so far all require you to have a chiral carbon in your molecule already, right? You have to set your chirality before you do this addition, right? It would be better if you didn't have to start out with a chiral carbon in your molecule, that you could use some sort of chiral reagent or chiral catalyst to install your chirality on a molecule that doesn't have any chiral centers. Right? So kind of the ideal, right, is if you have a double bond, right? And then you use a chiral catalyst. So to install a chiral center, right? So we make our catalyst chiral, and then we can take an achiral starting material and make it chiral, right? That's kind of the ideal, right? Because when you use a chiral catalyst, you don't need very much of the catalyst, so the chiral thing, you don't need a lot of it. And so you're able to take a very simple starting material and really introduce a lot of complexity, not only by what you added, but by the fact that you added it from one side as opposed to another. So we want to be able to use a chiral reagent or catalyst to install chiral groups on double bonds, right? You don't need any chirality in your starting material, which means you can start out with really cheap things and then install chirality in a step later on. Right? There are some of these that you need to have like an alcohol or some other functional group around to make it work, but that alcohol doesn't need to be chiral itself. It just needs to be there. Right? I'm going to talk about these reagents or these reactions and show you examples, but I am less interested in like thoroughly explaining how they work because there's a lot of moving parts to them. This is more to make you aware that these things exist. Partly for the whole molecule this semester thing, and partly just for general knowledge. So there's kind of going to be less mechanisms involved here, and more just like this is a thing that can happen, or this is a thing that you can utilize. So the first three that I'm going to talk about are all going to be grouped together because they were all developed by the same lab in the late 80s, early 90s. And these are the Sharpless dihydroxylation or Sharpless reactions. So at Scripps La Jolla, so Albuquerque, California, there is K. Berry Sharpless. And they spent a lot of time developing ways to do asymmetric additions to double bonds. And there are like 3 reactions that they are known for. The first is the dihydroxylation. I'm kind of doing these in almost reverse order of their discovery, right? So the asymmetric dihydroxylation, you're able to take an osmium tetroxide or an osmium reagent, and you do a dihydroxylation like we saw in like organic 1, where you add 2 oxygens to a double bond, but you introduce a chiral ligand so that the osmium itself is chiral. Right? Pro tip, I'm never going to have you like draw DHQ fall. Like, no thanks. I'd like to thank Wikipedia for letting me copy these so I didn't have to draw them. So one of these has quinine on it, and the other one has quinculadine. Quinculadine, I think. Or quinidine. Quinidine, there we go. And while they're not enantiomers, they're actually diastereomers of each other. So this part right here, this is the quinidine part, and this is the quinine part. And then the fall is the part that holds them together. Right? So if you look at this group here and this group here, they aren't enantiomers. They're diastereomers, but they act like enantiomers. So for chiral ligands, they're different enough that they give you the opposite enantiomer of your product. So if you remember Sweet Organic 1, though I don't know if I actually showed you this mechanism, right? The way osmium works, so the way osmium tetroxide works, OSO4, right? It makes a diol, but osmium tetroxide, that's backwards, you have 2 double bonds, right? Something like this, right? And you end up making a ring where you end up with OS you make this ring, and then water adds to this ring and knocks off the osmium and gives you your product. But what's nice is the osmium holds on to the oxygens the whole time. So, right, you're just having the osmium deliver the oxygens to the double bond. So if you can differentiate the 2 sides of the double bond, then you can say, then you can predict what enantiomer you're going to make. So in these Sharpless reactions, the DHQ fall, the ligand, star means chiral. So whenever you see like a ligand that has a star by it, it means that ligand is chiral. I'll actually use letters there, like whole words. Chiral. Right? So basically, all that happens is that ligand bonds to the osmium, and now the osmium is chiral. Right? So now you have a chiral thing, and one side of the catalyst is open, so the double bond can get to it, and the other side is closed. So you have your osmium with a chiral ligand on it, and the only way the double bond can approach it guarantees one side gets the alcohols and the other side doesn't. So I can so let's say you have your osmium tetroxide, right? It can be biology level explanation here, right? Here's my ligand, and let's say that ligand kind of blocks this side of the molecule. It goes like this, right? So when your double bond approaches, it can't approach like this because there's a steric interaction, right? The ligand comes down and is kind of poking in on one side. So your double bond can't orient itself this way, right? The double bond has to be oriented where now the group is on the other side. So you have to turn the double bond and put the group on the double bond away from the ligand. So now you've kind of set which side of the double bond can approach the osmium. So the ligand is just basically making a pocket, and the double bond has to orient itself so it fits in the pocket. And by doing that, you expose one face of the double bond to the catalyst, and the other face is hidden. and then that leads to your product. Again, this like third grader explanation of how chiral ligands work is all I need you to know. I just need you to know it works and it blocks a face. That's all I care about. So the sharpless dihydroxylation is super popular to the point where you can just order AD mix alpha or AD mix beta. So mix alpha has this ligand in it, mix beta has this, and then it has an osmium salt that is less bad for you than osmium tetroxide, and an oxidant to turn it into osmium tetroxide in solution. So you can just buy kind of pre-mixed what you need, you throw it in your reaction, and it works. So have a couple examples to show how these reactions work. Again, what I want you to take out of it is that you can take a double bond, you can pick your catalyst, your AD mix alpha or beta, and you can install chiral centers. So this, they use the AD mix beta and installed this side, and then they had to add more osmium and more ligand, and it installed the other side. You can overrule kind of inherent, you can sometimes overrule inherent substrate control and sometimes you can't. So here there were two double bonds. The sharpless dihydroxylation installed the chiral center that they wanted here. So the dihydroxylation of this double bond was reagent controlled. It was controlled by the catalyst. The dihydroxylation here, they couldn't overrule the inherent selectivity that the molecule had. Right? The molecule had a side it wanted the diol to be added from, and they couldn't overrule it with the catalyst. So they got one set that was reagent controlled and one set that was substrate controlled. And you can kind of see this, right? In the simplest sense, you have a group that is down and a group that is down, and you have hydrogens that are up. The hydrogens are small, so you're going to add from the side that has the smaller group, which has your hydrogens, has your diols coming from the same side as the hydrogens. Right, and then this is, which one's this? This is DHQ AQN is this guy here. Again, never going to ask you that, but I just wanted to, since it was a different catalyst, I just wanted to show, or different ligand, I wanted to show what it was. Right, and then here's another example where I apparently didn't change the product. Good job, me. 1 second, let me fix that. Oop. Wow. It's just the starting material over again. Good job. Hey man, I'm making these slides and babies are screaming at me. I can only do so much. So let me fix this real quick. I think it should be, it's up. And it somehow got bigger, which is great. Okay. It's fixed now. And then we're going to do this. All right, cool. There we go. We fixed it. There you go. So here you're installing your double bond. Your alcohol is here. Now there's other chirality, right? There's a chiral center here. There are chiral centers kind of all around the molecule. But the ligand, they're far enough away, and the ligand is strong, has a strong enough preference that you're able to override those other chiral centers, or they're too far away to matter. So like the catalyst overrules this chiral center right here, but then these other chiral centers are too far away to actually interact with the catalyst. So after the dihydroxylation, the Sharpless group developed an amino hydroxylation where you can add a nitrogen to one side of your double bond and an alcohol to the other. Right? So you have your double bond. You're able to add amine to one side, alcohol to the other. And again, depending on the ligand, you can make one enantiomer or the other. So this works best if you have an electron withdrawing group on your double bond, which makes sense because it polarizes the double bond. It changes the sides of the double bond. So what I mean by that is if you have something like this, both sides of the double bond are very similar, right? Both carbons have the same charge. When you put an electron withdrawing group on your double bond, say like a ketone, right, you have a resonance structure where you take electrons away from one side of your double bond, and that carbon of your double bond is positive, right? It's positive in a resonance structure. So that means we can think of this double bond as having a positive carbon, right? So now I've differentiated my sides of my double bond, right? One side of my double bond is positive. One side of my double bond is more neutral. So it's easier to predict where you're going to add a group because the thing that's most nucleophilic, the thing that wants to add to the more positive carbon, is going to want to add to this carbon because this carbon is more positive due to resonance. Right? So in these reactions where you're adding two different things, right? You're adding an amine and an alcohol. Right? Putting an electron withdrawing group on your double bond makes it so one side of your double bond is positive and one's more neutral. So you're more able to predict which side's going to get the oxygen and which side's going to get the nitrogen. That said, regioselectivity, again, which carbon gets the oxygen, which gets the nitrogen, is hard to predict. So the amine normally goes to the most substituted carbon. So the carbon that can best stabilize positive charge. But in cinnamate esters, they normally go to the beta carbon. So if you think about, which makes sense, right? So a cinnamate ester, for the people, right? I don't know why it's orange. So this is cinnamic acid. It's like a big part of cinnamon. There's cinnamic. Right? Cinnamate esters. Oops. Right? You just turn it into an ester. That's a cinnamate ester. So what it's saying is that normally, under these conditions, you get the nitrogen on the beta carbon, the oxygen on the alpha carbon. Now, I say this, in the first two examples I show you, this switches. And it just kind of switches based on the ligand. So the protecting group, this X that is on the nitrogen, impacts the reactivity. So depending on what that X group is, changes both selectivity and reactivity. So the X group, so the first three, yep, are sulfonamides. Oh, I should probably switch over there. So these three right here, bus, meso, and nozzle, are sulfonamides. So those are things that have S double bonded to two oxygens. Right. So, like, let's look at so bus is an S double bond O tert butyl. So if you have like R or sodium, there you go. So like this, so this is bus. Okay, this is a sulfonamide. And then you have like nozzle, NS, the nozzle. They get really ugly. And you have a nitro group. So those are sulfonamides. Those are slightly less reactive. The other version of this are carbamate protecting groups. So these are sulfonamides, right? And then you have carbamates. Oops. Bam. Be a molecule. Bam. Is that what they were yelling at Coastal Games? Bam. No. Be a molecule. It might have been something else. Very disappointing. Right. Carbamates are R, O, double bond O, N, R. So the name of the carbamate changes based on what the R group is. So when you see Bach is tert butyl. CBZ is a benzyl, right? So depending on what the group was on the nitrogen, changed how the nitrogens reacted. So, some examples from the literature / my book that I have at home. Hey, buddy, change the slide, change the screen. You can do it. I have faith kind of in you. There we go. I kind of have faith in him. All right. So here, one thing is that there's not a pre-mixed thing that you can buy, like Admix or AdMix alpha or beta, or you just kind of have to throw everything together. So you have here they made the. So I guess I should point out before I go on. Sorry. Right. So what happens is what you need an oxidized nitrogen. So it needs to have a halide on it, usually a chlorine, and then it has its whatever its protecting group is. Either it's sulfonamide or carbamate, right, on it. But you need to have this nitrogen halide bond to make these work. So in this first example that I have, they don't start with the nitrogen chlorine bond. They actually use sodium hydroxide and tert butyl, whatever this is. I'm having a hard time reading it. I'm getting old. Right. This step here generates that carbon chlorine bond, and then the rest of this, the osmium, salt, and the ligand, do the dihydroxylation. So I just said that the amine prefers to go beta, but it depends a lot on the ligand. So here it goes to the alpha carbon, but then I do it slightly differently under slightly different conditions, and I get the expected beta product. So it just depends. And again, there's chirality in this molecule over here. But since it's on the other side of the aromatic ring, it's like 1,000,000 miles away. So this double bond doesn't see those chiral centers. So this is purely controlled by the ligand. And you notice here that I'm saying that it's a 91:9 diastereomeric ratio. That's because I can't give you an EE because I have other chiral centers, right? So I'm making diastereomers. So that's why it's a diastereomeric ratio as opposed to just like an enantiomeric excess. So basically I'm getting 91 of this diastereomer where the nitrogen and oxygen are on a wedge and 9 of them being on a dash. Same thing down here. Here they started with their salt already, or their chlorinated amine ligands, and now this switched selectivity. But again, these chiral centers are super far away, so this is all just controlled by the ligand. Right? So then here I have styrene derivatives. And again, we're able to install that one chiral center in 94% EE. And then here we install this nitrogen chiral center, again, 94% EE. I think we've done enough for the day. We'll call it, and I'm going to make an executive decision right now. That executive decision is we're not going to have class on Tuesday. You can use that time to work on your test.